Welcome to today's statistics tutorial. Today we're going to be discussing hypothesis testing with two samples. See the links below for the link to the online calculator we will be using with this tutorial, as well as additional supports and resources.
Today we are doing Statistics Module 10, which is hypothesis testing for two samples. So there's two types of testing. The first one is going to be for independent groups, where the samples are independent. We'll have a test with two population means or a test of two population proportions. And that will be, we'll have it with both with known and unknown population standard deviations. And then the second type will be if we have a matched or paired group, and that's when the samples are dependent. And this can be a test of two population proportions by one test of population mean differences. So those are what we're going to look at today. So the first type we're going to look at is having an independent sample with unknown population standard deviation and two population means. With this, let's look at your formula. So let's first write this down. So it's going to be independent. You're going to have two population means and an unknown standard deviation. So the random variable is going to be the difference of your sample means, and that's and it's going to be your distribution is going to be the student P distribution with your degrees of freedom where the variances are not pooled. So let's look at what these formulas are. So this is going to be your first thing is you're going to get your differences of your two means, and that's going to give you a mean for your difference. So mean of the differences. Then your standard error, or your standard deviation is going to have the formula of the square of the first sample divided by the square root of sample 1 plus the square of the sample standard deviation of the second sample divided by the square root of sample number 2. And that is your standard deviation of the mean. Your test statistic, which is your t-score, t-score is going to have the formula of the mean, the sample mean of the first sample minus the sample mean of the second minus the population mean of the first minus the population of the second. And oftentimes we're going to set these two equal to each other, which means that this difference is just going to be 0. And then the bottom is just the standard error, your standard deviation, which is the same formula. It would be the same formula. I think those square roots are not quite right. And this is called the Aspen-Welch t-test. Yeah, this is not quite right. So these square roots that are right here, this is a typo in your book. So it should just be N. Okay. And then your N values are your sample size, your degrees of freedom, which is your DF, is going to be at the formula S1 squared divided by N1 plus S2 squared divided by N2 to the second power all over 1 over N minus 1 times sample squared divided by, the standard deviation squared divided by the sample, that whole quantity squared, plus 1 over the second sample minus 1 times standard deviation squared divided by the second sample size, all of that squared. So let's do an example so we can see how all of these formulas work together with our hypothesis test. Okay, so we have a study that wanted to measure the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. A study is done and data are collected, resulting in the data in the table below. Each population has a normal distribution. So let's take a look at what we have. So what we're given is, with the girls, we have a sample size. We're going to use G as our to denote the girls and B for boys. So the girls had a sample size of 9. The sample mean is the average number of hours playing sports per day is 2. And the sample standard deviation is going to be 0.866. Oh, and it just all disappeared. Let's see if that comes back. And then for the boys, the sample size for the boys is 16. The mean is going to be 3.2. And the sample standard deviation is going to be 1. I don't know if those numbers are going to come back or not. Let's see if it's. Okay. Now we want to know, is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day, and we want to test at the 5% level of significance. So that means our alpha is going to be 5%, which is the same as 0.05, which means we have a confidence level of 95%. And then that tells us, so if I have a 5% That's going to give me a z-score of, actually that's not quite what I want. So this, so before I do that, actually, so this is a test of two independent groups and with two population means. Our null hypothesis is going to be, we're going to say that the mean of the girls is going to equal the mean of the boys, which is the same as saying that the mean of the girls minus the mean of the boys is going to equal 0. And then our alternate hypothesis is going to say that the mean of the girls does not equal the mean of the boys, which is the same as saying that their difference does not equal 0. Now, because we're using equal, that tells me it's going to be a two-tailed test. So when I'm figuring out my alpha, it's going to be actually alpha over 2. This is 95%. And then this is alpha over 2. So alpha over 2 is 0.025. And then if I want to find my z, of z of alpha over 2, we're going to set that equal to 0.025. And that's going to give me a z-score for when I have a two-tailed test. It's going to be 1.96. Okay, so this z is 1.96 for this end, and it is a minus 1.96 on the opposite end, and this alpha is a 0.025. Okay, so this is what we're going to be comparing. This is the standard normal distribution, and this is what we're going to be comparing to help us determine is our p-value. So what we're looking for is we want to know, is our p-value, or is the probability of going to be less than or greater than this critical value of the z-score of 1.96 and the probability of 0.025. So now we're going to go ahead and plug in some numbers. So if I have the mean of the girls minus the mean of the boys, that's going to give me 2 minus 3.2, which is going to give me a minus 1.2. Okay, so if I have a mean of 1.2, so that means on this graph, the comparison graph, the population is 0, and then I got a difference of minus 1.2, and then I know it's a two-tailed test because it's equal. So that means I can also look at my other point is 1.2. And then I'm going to want to find my z-score and my p-value for when my mean, because this is the differences in the mean, when the differences in the mean is going to be at positive and negative 1.2, I want to know what my z-scores are and what my p-values are so I can compare them to this critical value to determine, is my null hypothesis, do I want to reject or not reject the null hypothesis? So now let's do my standard error, standard deviation. Plug that in. That's going to give me, I'm going to have the standard deviation of the girls squared. It's going to be 0.866 squared divided by the sample size from the girls, which is 9, plus standard deviation of the boys divided by the sample size of the boys, and then take that as a square root. And that's going to give me 0.380, excuse me, 18. Now I'm going to get my T statistic, which is going to be the differences of these two means. So that's going to be my minus 1.2 minus the difference in the population mean divided by the deviation, which is going to be 0.3818. And that is going to give me a minus 3.14 for my z. So that means this z here is a minus 3.14, and my z up here is going to be a positive 3.14. How did you come up with the 0? Okay, so this, let's write that formula out. So this is my z, the mean of the girls, minus the mean of the population, minus the population all over the standard deviation. So we saw right here, if our null hypothesis, if we set these two, if we're going to say that these are, we're going to claim that these two are equal to each other, then if we take the difference, that difference is 0. So this is where that came from. That's going to give me a 0 here. And then this right here is going to give us our minus 1.2. Okay? Any questions so far about the formulas? Just for space, I'm not rewriting the formulas. But this is what we use for our test statistic. This is what we use for our standard deviation. And this is what we use to get our mean. Okay? So now we have our first test. So we have the first test that we can do is we can compare our z values. Because the first test is the absolute value of z if it is greater than our z of alpha then that tells us we're going to reject the null hypothesis. So then let's look and see what we have. So we have 3.14, and we're going to compare it to 1.96. So this is true. The 3.14 is bigger or more extreme than the 1.96. So this, with our Z test, that's going to tell us we're going to reject our null hypothesis. Okay. So now we're going to do our second test. We're going to find our p-value, and we're going to do our test of the critical value and compare it to the p-value, and we should get the same rejection to reject the null hypothesis. So you have two tests to verify whether or not you're going to reject the null hypothesis. So I'm going to move this board to the side. Okay, excellent. I'm going to put okay, so I'm just going to go ahead and get a new board because I'm running out of room. Okay, so let's write what we have just so that we're staying consistent with all our information. So we have the sample size of the girls. The sample size of the girls is 9. The sample size of the boys is 16. The mean of the girls is 2. The mean of the boys is 3.2. Our standard sample deviation of the girls is 0.866. Sample standard deviation of the boys is 1. And then we got that our significance level is at 5%. It's a two-tailed test, which means that it's split, which means our alpha over 2 is going to equal 0.025, and that's going to give us a z-score of 1.96. We have an unknown population. We found that the differences of the means. So the differences of our means we found that to be 1.2. The differences of our standard deviations, that gave us 0.3818, which was our formula for our standard error. And we got a test statistic of minus 3.14. And we showed that our t-score, the absolute value of our t-score, was greater than the absolute value of our z of alpha over 2. So that was 3.14 is greater than 1.96. So that's what we've calculated so far. So now we're going to do our degrees of freedom. And that's a pretty big formula. That's the standard deviation of the girls squared divided by their sample size plus the standard deviation of the boys squared divided by the boys sample quantity squared. divided by 1 over the sample size of the girls minus 1 times the standard deviation of the girls squared divided by the sample size of the girls, and that whole quantity is squared, plus 1 over the sample size of the boys minus 1 times the standard deviation of the boys squared all over the sample size of the boys quantity squared. We're going to plug in those numbers, so that's going to be 0.866 squared for the girls all over 9 plus 1 squared over 16 for the boys. Take that quantity squared. And on the denominator, we're going to have 1 over 9 minus 1. And then once again, we're going to have 0.866 squared all over 9. And this whole quantity is going to be squared. We're going to subtract that from 1 over 16 minus 1. 16 minus 1 times 1 squared over 16, and that quantity squared. And then when we plug in all of those numbers, we're going to end up with 18.85. Okay, so now we're going to use the online calculator. We're going to put in we're going to do the t-distribution with 18.85 degrees of freedom. The mean is going to be 0. Standard deviation is going to be 1. And then we're going to do the probability that x is going to be less than our t-score, which was a minus 3.14. And when we calculate that, that is going to give us, so this is the probability. So we're finding the probability that x is going to be less than minus 3.14. And that is going to give me a probability of 0.0027. Okay. Now, if you remember, because we're dealing with the p-value, because we have a two-tailed, this is going to be half of our p-value. It's going to be 0.0027. And then the other half of our p-value is going to be on the other side. Just like we split up the two alphas. So then to get our true p-value to compare to alpha, we're going to take our p-value, we're going to take 2 times 0.0027, and that is going to give me 0.0054. So now I'm going to have my second test, which is we want to know if alpha is greater than our p-value, then we're going to reject the null hypothesis. So my alpha was 0.05, and my p-value is 0.0054. So this is true. So that tells us we're going to reject the null hypothesis, which is the same as what we got up here, which told us based on the t-scores that we were going to reject the null hypothesis. So what that tells us, our conclusion is at the 5% significant level, the data shows sufficient evidence to conclude that the mean number of hours girls and boys aged 7 to 11 play sports per day is not equal. Those are going to be different values. Any questions about how I calculated any of that data or how I came up with those conclusions? Okay. So that is how you are going to solve when you have an unknown population standard deviation. So now let's go ahead and we're going to do another one, and then we're also going to let's do a second example, and then we're also going to do at the end of the second sample, we're going to look at Cohen standards for small, medium, and large effect sizes. Okay, so in this problem, it says a study is done by a community group in 2 neighboring colleges to determine which one graduate students with more, who graduates more students with more math classes. College A samples 11 graduates. Their average is 4 math classes with standard deviation of 1.5 math classes. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1 math class. The community group believes that a student who graduates from College A has taken more math classes on the average. Both populations have a normal distribution. Test at the 1% significance level. Okay, so let's write out what this tells us. So I have College A has a sample of 11. Its mean is 4, and its sample standard deviation is 1.5. With College B, my sample size is 9. My mean is 3.5. And my sample standard deviation is going to be 1. Now, they've given us a significance level of 1%. So that's equal to 0.1, which means we're looking for a confidence level of 99%. This is a test of 2 independent groups with 2 population means, and the population standard deviation is unknown. Now, our sample size, if you notice, our sample size of NA plus NB is going to be 11 plus 9, which equals 20. And that is less than 30. So anytime your sample size is less than 30, that tells us we're going to use a t-distribution with degrees of freedom in order to approximate the normal distribution. So let's look at our data. Our random variable, the difference of our mean of the number of math classes is going to be 4 minus 3.5, which equals 0.5. Our null hypothesis, we're going to say our null hypothesis is that the mean of college A, we're going to say is less than or equal to the mean of college B. And our alternative is going to be the opposite, is we're going to say that the mean of college A is going to be greater than the mean of college B. So in words, our null hypothesis is saying students who graduate from college A have taken the same or fewer math classes as students from college B. And then our alternative hypothesis is students who graduate from college A have taken more math classes than students at college B. Now, if you'll notice in the questions, it says the community group believes that a student who graduates from college A has taken more math classes on the average. So once again, if you remember from last week, that whatever the claim is, we will usually make that the alternative hypothesis, and then we're going to make the opposite be the null hypothesis that we're going to determine whether or not we're going to reject or not reject based on the sample data. Now, because we've got because we have the equal sign here, then we can say that A, part of our null hypothesis is that A is going to equal B. Let's see. Go back. So right now we have this equation, and then based on our using algebra, if I subtract that, we can set that difference equal to 0 because we have that equal sign there. And then this bottom number, because our alternative hypothesis is greater, has the greater than sign, that tells us this is going to be a right-tailed test. If this had been a not equal sign here, then that would have made it a two-tailed test. Okay. So what we're looking for is we're going to assume the population mean is 0, and then the differences of our sample mean was 0.5. So we're wanting to know what is the probability that when we take samples that our mean is going to end up in this shaded area. Okay, so let's do our standard deviation, which has this formula of the standard deviation of college A over the sample size college A plus the standard deviation of college B squared over the sample size of college B. So that is going to give me the square root of 1.5 squared over 11 plus 1 squared over 9. And that square root is going to give me an answer of 0.3627. And then I'm going to solve for my p-value, my t-statistic, which is going to be the difference of the sample means minus the difference of the population means all over our standard of error, the standard deviation. So that's going to give me 0.5 minus 0 divided by 0.3627 with a final answer of 1.38. Okay. Now this is a right-tailed test, so let's look at the z-score for alpha. The z-score of our alpha is going to use a normal distribution, mean of 0, standard deviation of 1. And we want to know if x is going to be greater than 0.01. So that means my z-score for my critical value is going to be 2.33. So now I have my z-score and my t-score, so I can do my first test, which I'm going to compare. I want to know if my t-score is greater than my z-score of alpha, then I'm going to reject the null hypothesis. So I have my t-score is 1.38, and my z-score is 2.33. My z-score, my z of alpha is greater, so this is going to tell me to do not reject the null hypothesis. Okay. So now let's find the probability, the p-value based on the t-score that we calculated, and then that will give us a second test to see if we also get a do not reject based on the p-value, which will also confirm that we did all of our calculations correct. So because my sample size is less than 30, I need to do my degrees of freedom calculation. And that's going to be my standard deviation of sample A squared all over the sample size plus standard deviation squared of the second sample over its sample size, quantity squared, 1 minus sample size minus 1 for the first one, standard deviation squared divided by sample size for the first quantity squared. Then we're going to do the same thing with sample size with the second sample. And then when I plug in those numbers, that is going to give me a 1.5 squared over 11 plus 1 squared over 9 quantity squared divided by 1 over 11 minus 1 all over 1.5 quantity squared divided by 11. This quantity is going to be squared plus 1 over 9 minus 1. And then this is going to be a 1 squared over 9 quantity squared. And then when I calculate all of those numbers, that's going to give me a degrees of freedom of 17.4. So now I'm going to go to my online calculator in my degrees of freedom. I'm going to put 17.4. My mean is going to be 0. Standard deviation is going to be 1. Now I'm going to find the probability that X is going to be greater than 1.38 to get my p-value for the z-score of 1.38. And that is going to give me a probability of approximately 0.09. So now we're going to look at our formulas again. If alpha is greater than our p-value, then we're going to reject the null hypothesis. So let's look at the alpha that we were initially given was a 0.01. So I have 0.01, and I'm going to compare it to 0.09. 9 is greater than 1, so that's going to tell us to do not reject the null hypothesis. Okay? So what that tells us is at the 1% level of significance from the sample data, there isn't sufficient evidence to conclude that students who graduate from college A have taken more classes than students from college B. Any questions about how I got any of these calculations or conclusions? Okay, now let's take a look at Cohen's standard for small, medium, and large effect sizes. So the Cohen D is a measure of the effective size based on differences between two means and measures the relative. How do you calculate the zero from the mean? Okay, so are you looking at this right here? Is that what you're talking? Yeah. Yeah. So because we set this, so this is the easiest way to remember is this is usually going to be 0. And it's because anytime you have the null hypothesis is always going to contain the equal sign. And so if you don't know what these are, it's going to be either less than or equal to. So if these two numbers are equal to each other, then when you subtract them, it's always going to be 0. So if you do not know what the population mean is, you're just it's just automatic, for the most part, it's automatically 0. And I think it's more of just a technicality that it's put in the formula just to stay consistent with the definition of a t-score. So if you remember from module 6, the definition of a z-score was the sample was the value minus the mean divided by the standard deviation. So this formula, by keeping this here, then we're just staying consistent with the formula. Even though this is 0, you could technically just write it as the mean divided by the standard deviation, and it's going to be the same, but it's just they're staying consistent with the formula based on everything that we've done before. And so that's why it's written the way it is. But yeah, it's going to always be 0 because we have the equal sign in the null hypothesis. And then the way that they say it in their book is they just say it is generally equal to 0, but I've never seen when it's something else. Good question, though. Thank you. Any other questions that need clarification? Because there's a lot of formulas with these problems. Okay, let's continue on to Cohen's D. So Cohen's Z is a measure of the effect size based on the differences between two means and measures the relative strength of the difference. The calculated Z value of effect size is compared to Cohen's standard effect sizes. So the first thing you're going to do with this Cohen's Z is you're going to do a calculation. So the D is going to be the difference in the means divided by S pool. And S pool is going to equal the square root of n minus 1 standard deviation of the first. So this is the first sample plus the sample size of the second minus 1 times the sample deviation of the second squared, all divided by sample 1 size plus sample 2 size minus 2. So then if we plug in the numbers that we've been working with before, then let's get this S pool, which is going to be the square root of the first one. College A had a sample size of 11, so it's going to be 11 minus 1 times the standard deviation of 1.5 squared plus the second college, which is going to be 9 minus 1 times 1 squared, and that's going to be over the sample sizes 11 plus 9 minus 2. And then when we do that calculation, we get okay. So then when we do that calculation, we end up with 1.3017. So then when I go to solve for D, I'm going to take the difference in the mean. So that's going to be 4 minus 3.5 divided by this 1.3017, which is the same as 0.5 divided by 1.3. And that's going to give me 0.3846. So this is my calculated Cohen Z. And then I'm going to compare it to the Cohen's standard effect sizes. So the size of the effect, so he's going to have small, medium, and large. And then for a small, you've got 0.2, medium is 0.5, and large is 0.8. And this is, so you're looking at the size of the effect is small, medium, or large, and then we're comparing it with the D value. So now what we're going to do is we're going to compare this from the standard effect sizes with the calculated value that we got. So we got a calculated value of 0.3846. Well, that's going to fit somewhere in between small and medium on the Cohen standard effect sizes. So that tells us the effect is small because 0.384 is between Cohen's small and medium effect size values. The size of the differences of the means of the two colleges is small, indicating that there isn't a significant difference between them. So this is just further supporting what we found using the p-value that there was insufficient evidence to conclude that there was much of a difference between the two schools. Okay? Any questions? Okay, let's go ahead and we'll get a new board. And this time we're now going to move on to two population means with known standard deviations. And these are also independent samples. Okay, so with this, so we're going to have two population means, so it's going to be independent. We're going to have two population means, known standard deviations, okay, so for this, the formula is our notation of x1 minus x2, the random variables, is approximately normally distributed with the differences of the mean as your mean, and then your standard deviation is going to be the square of the first population divided by the sample size plus the square of the second population standard deviation divided by the sample size of the second, all squared. And your z-score is going to be the difference in the means, the sample means, minus the difference of the population means, all over the standard deviation, which is, and this actually, even though there's a plus sign, when you do the calculations, this is actually also the difference in the standard deviations. But when you do all the math to get this, generate this formula, it ends up being a plus just because of those squares. And if you watch the Khan Academy videos, you can walk through how these different formulas are derived. And then generally, our mu1 minus mu2 is going to equal 0. Okay, so let's do an example. Okay, so in this example, it says independent group population standard deviations known. The mean lasting time of two competing floor waxes is to be compared. 20 floors are randomly assigned to test each wax. Both populations have a normal distribution. The data are recorded in the table. So let's take a look at what we have here. So we have wax 1 and wax 2. Both of them are going to have a sample size of 20. They say 20 floors were used, were tested. Each wax was tested with 20 floors, so that both shares have equal sample size. The mean of the first one is going to be 3. The mean of the second is going to be 2.9. The population standard deviation for the first is going to be 0.33. The population standard deviation of the second is going to be 0.36. And this says, does the data indicate that wax 1 is more effective than wax 2 tests at the 5% level of significance. So that means we're going to have a level of significance of 0.05, which means we have a confidence level of 0.95. We're going to set up our and so this we have, so let's set up our null hypothesis and alternative. So our null hypothesis is that the mean of the first wax is going to be less than or equal to the second, and the alternative is that the mean of the first is greater than the second. So in words, this is saying the first one says that the wax 1 is equal to or less effective than wax 2. And the second one is saying that wax 1 is more effective than wax 2. Now, because we have in our alternative, we've got the mean of 1 is greater than mean of 2, then that tells us this is going to be a right failed test. Okay, so, and we've got that the differences of the population means, those are going to be 0. The differences of the sample means is going to be 3 minus 2.9, which is going to give me 0.1. So on my differences of the means, this is going to be 0.1. And we're going to solve for a z-score for this. On our critical values, we're going to have an alpha of 0.05 with a 95% confidence level. So let's find out what that z-score is. If I have normal distribution, mean is 0, standard deviation of 1. I want to know what the probability of a critical value being greater than 0.05. That means my z-score for my alpha is going to be 1.65. Okay, so now let's look at our standard deviation or the standard error, which is going to be the square root of the population mean squared for the first wax divided by the sample size of the first wax plus the standard deviation squared of the second wax divided by the sample size of the second. And then the square root, sum them and square root them, and that's going to give me a standard deviation of 0.10920. Then when I get my t-score, actually, and this is a z-score, so our sample sizes, we've got 20 plus 20 equals 40. That is greater than 30. So that tells us we can do a normal distribution rather than a t-distribution. So my z-score is going to be calculated getting the differences of the two sample means, which is 0.1 minus the difference of the population means, which was 0, divided by my standard deviation, which was 0.10920. 0.092, and that's going to give me a p-score of 0.91575. So now I'm going to put this in my online calculator. Normal distribution, mean is 0, standard deviation of 1. I'm looking for the probability that x is going to be greater than my z value of 0.9157. Probably don't even need that much. Probably that. What did I have? 575. We'll just put all it in. Okay. So then I'm going to have the probability that x is going to be greater than that 0.91575. That's going to give me a p-value of 0.1799. So that's the probability that that is the probability that any of my scores or any of my average means are going to fall within the shaded area. So now I'm going to do my two tests. So my first test is I'm going to test to see if z is greater than z of alpha. So I had a z-score of 0.91575, and my z of alpha was 1.65. So it is the opposite. So that would tell me, so if it has this, if my z-score that I calculate is greater than the z of alpha, I'm going to reject the null hypothesis. This is not, it's the opposite. So that's going to tell me to do not reject the null hypothesis. And then I'm going to also check it with my alpha and p-values. So the rule is if alpha is greater than my p-value, then I'm going to reject my null hypothesis. So my alpha that I was given was 0.05. My p-value is 0.1799. 0.18 is greater than 0.05. So that's going to tell me do not reject the null hypothesis. So what that tells me is the conclusion is at the 5% level of significance from the sample data, there is not sufficient evidence to conclude that WAC 1 is more effective than WAC 2. Any questions? So this next one is comparing two independent population proportions. So these are going to be independent population proportions. Now, in order to do this, we want our P, which is our successes, needs to be greater than or equal to 5, and our Q needs to be greater than or equal to 5. if it has that, and the population size has to be 10 times or 20 times the size of the sample. If we have those qualifications, then we can approximate a normal distribution using the binomial principles of success and failure. So with this, we're going to have a normal distribution. Our null hypothesis is going to say that P of A is going to equal to P of V, which is the same as saying P of A minus P of B equals 0. So the distribution, then we have the distribution for the differences is going to be P prime of A minus P prime of B is a normal distribution with mean, or the differences between the successes of the two is going to be 0. And the what we're going to use for standard deviation is going to be the proportion C minus 1 minus the pooled proportion times 1 over the sample of A plus 1 over the sample of B. And our test statistic P, our test statistic, excuse me, that should be a Z, is going to be P prime of A minus P prime B. Remember that the prime is the estimated proportion minus the population portion of A, the population portion of B, all divided by the square root of P, the pooled 1 minus pooled 1 over the sample of A plus the sample size of B. Okay, and let's go ahead and do a example. Okay, so for this one says 2 types of medication for hives are being tested to determine if there's a difference in the proportion of adult patient reactions. 20 out of a random sample of 200 adults given medication A still had hives 30 minutes after taking the medication. 12 out of another random sample of 200 adults given medication B still had hives 30 minutes after taking the medication. Test at the 1% level of significance. So let's see what we have. That means for medication A, we have medication A and medication B. The number of successes, our X for A is going to be 20. Our X of B is going to be 12. Our sample size for both of these is 200 each. We're given a significance level of 1%. That equals 0.01. That means we're having a confidence level of 99%. Our random variable, which is our p prime of A minus p prime of B, is going to be the difference in proportion of adult patients who did not react after 30 minutes to medication A and B. In other words, that they still had hives. So this first one, your x's. So your P of A, your P prime of A is going to be x of A divided by the sample size of A. So that's 20 over 200, which is 0.1, which means our Q of A, remember, is 1 minus P of A. Actually, we'll need, and we won't need this, so I'm not going to go ahead and calculate that, but just remember that your failures are just the opposite. Let's go ahead and get my P prime of B is going to be the number that didn't react for B over the sample size of B, which is going to be 12 over 200, which is 0.06. So now if I want the difference of these two, 0.1 minus 0.06, which is going to give me 0.04. My hypothesis, my null hypothesis, is going to say that the population proportion for A is going to equal the population portion of B. And I've got P of A minus P of B is going to equal 0. And my alternative is going to be the opposite. So that's going to be my P of A does not equal P of B, which means that their difference does not equal 0. Okay, and then my pool is going to be x of A plus x of B divided by n of A plus n of B. So that's going to give me 20 plus 12 all over 200 plus 200 is going to equal 0.08. And 1 minus P of C is going to equal 0.92. So going up here, writing the pooled. So this is the pooled portion. And it looks like, according to my notes, it looks like your book has the equations written in a couple of different ways. So that's something you want to kind of be careful of. But it's going to be the x of A plus x of B all over n of A plus n of B. So now we're going to go, we've got the PC, we've got our P minus A. so now we're going to get our standard deviation for our proportions, which is going to be, I'm just going to, and that is going to be our PC times 1 minus PC times 1 over the sample of A plus 1 over the sample of B. So that's going to equal the square root of 0.08 times 0.92 times 1 over 200 plus 1 over 200. And when we do the calculation, that's going to give me a 0.02713. Any questions so far? So if you'll remember, these formulas are just coming from our binomial theorem that was using successes and failures. We use successes, failures, and sample size to get all of these equations. Then my Z statistic is going to be my P prime of A minus P prime of B minus the difference between my population proportions and then this on the bottom is just going to be your standard deviation that we just calculated. So we saw this difference was 1 minus 0.6, so this is 0.04 minus 0 divided by 0.02713. Any questions about where these numbers came from? Okay, and that's going to give me a 1.474 for my Z statistic. Okay, and then they gave us up here, they gave us a significant value of 0.01. So let's calculate what that is. Because we've got the equal signs, that tells us it's going to be a two-tailed test. So a half alpha, half of an alpha is going to be 0.005. The probability that X is going to be greater than 0.005 is going to give us our Z value. So that means my Z of half alpha is going to be 2.58. So now I can do my first test, which is if Z is greater than my Z of alpha, then I'm going to reject the null hypothesis. So my Z is 1.474, which is less than the Z score of my critical value. So that's going to tell me do not reject the null hypothesis. And now I'm going to get my I am going to figure out my p-value. Now my z-value, we have a mean of 0. We have a sample mean of 0.04, which we now have calculated to have a z-score of 1.474. And then we want to know what the p-value is for the probability that the value is going to fall in that area. So we can use our z-score that we just calculated, and that would be with a normal distribution, mean of 0, standard deviation of 1. We're going to look for x greater than 1.474. And that is going to give me a p-value of 0.0702. So this would be the probability that x is greater than 1.474. It's going to be 0.0702. Now, if you remember, because we had the equal sign, that tells us it's going to be a two-tailed test. So that means that this is also going to be the same for the value of 0.04 and the z-value of a negative 1.474. So that p-value is also going to be the same as 0.702. These are half values, so in order to get the total p-value, I'm going to need to, so this is a half of a p-value. Then I'm going to need to multiply that by 2, which is going to give me a p-value of 0.1404. And then just also to show you that so that's for our z-value, but we could also have used the 0.4 value with the given standard deviation. So if I have a normal distribution, the mean is 0, standard deviation is 0.02713. Then I could have also found my p-value by plugging in x greater than 0.04, and that's also going to give me that same number of 0.0702. Okay, any questions about how, so that's the second way that you can verify your p-value. And then you want to remember that we're going to add these two together to get the total p-values because these are half alphas. So then we want to say then we do our second test, which is if alpha is greater than our p-value, we're going to reject the null hypothesis. So my alpha, they gave us a significant level of 1%, and we just calculated our p-value to be 0.1404. 14 is greater than 1, so that means we're going to say do not reject our null hypothesis. So what that tells us is at the 1% significance level from sample data, there is insufficient evidence to conclude that there is a difference in proportions of adult patients who didn't react after 30 minutes to medication A and medication B. Any questions? Okay, let's go on to the last section. And the last section is going to be match or paired samples. And these are dependent. The samples are dependent on each other, where all of our previous ones are independent. These are dependent. The sample sizes are usually small. The samples are drawn from the same pair of individuals or objects, and the differences are calculated and compared. For these type of tests, we're going to use the student p-distribution for a single population mean and a n-1 degree of freedom, where n equals the number of differences. So let's do an example. So for this type of problem, we're going to use our p statistic is going to be the mean of the differences minus the population differences divided by the standard deviation of the differences of the sample divided by the square root of the sample size. Okay. So this one says a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results for randomly selected subjects are shown in the table below. A lower score indicates less pain. The before value is matched to an after value, and the differences are calculated. The differences have a normal distribution. The question is, are the sensory measurements on average lower after hypnotism? Test at the 5% significance level. So we're given a significance level of 5%, which equals 0.05. Our sample is the data. So in order to do this type of equation, we're going to subtract the before data from the after data to get the difference of each pair. Then the differences become our sample. So they're going to take the after data, subtract the before data, get the difference, and then this new list of difference is now the data that you're going to use, your sample data that you're going to test. So in this sample, I now have a sample size of 8 because it's the differences is my sample. Then I'm going to calculate the sample mean, which if you remember from Module 2 is the summation of the x values divided by the size of the sample. And so that sample mean is going to be a minus 3.13. And the sample standard deviation, once again from Module 2, is going to be the square root of the summation of our values minus the mean quantity squared all over the sample size minus 1. And then for this set of data, I'm going to get a sample of the standard deviation of the samples is going to be 2.91. My null hypothesis is going to be to say that the mean of the differences is going to be greater than or equal to 0, which means that there's not going to be any change or improvement after hypnotism. So this says there's some or more pain felt after hypnotism, and then my alternative is going to be that the mean of the differences is going to be less than 0. So that means there's going to be less pain after hypnotism and that the subjects are going to show improvement. So our score should be lower, so the differences ought to be negative in order to indicate improvement. We're going to use the student's p-distribution. So our degrees of freedom is going to be 8 minus 1 is going to be equal to 7. Then I'm going to use my p-score is going to be my mean of the differences, which is my minus 3.13, minus the mean of the differences, which is going to be 0. And we get that from right here. That's why we can call this 0, because we have that equal sign. Then we're going to divide it by the standard deviation of the sample divided by the square root of the sample size. And then when I do that calculation, I'm going to end up with a minus 3.04. So now I'm going to do my calculation. I'm going to use the t-distribution, 7 degrees of freedom. My mean is 0, standard deviation is 0, and I want to solve for the probability that x is going to be less than minus 3.04. There we go. Okay, so you're going to calculate doing the t-distribution with 7 degrees of freedom. You've got your mean is 0, standard deviation of 1. Then you've got your p-value. You're looking for x less than negative 3.04. That's going to give you a probability or a p-value is going to equal 0.0094. So we're looking at our little chart. So we've got 0, we've got a minus 3.04, which gives me a p-value of 0.0094. Okay, so this is my p-score, and my this. So this would be, so this point here for my mean is my minus 3.13, and then for my t-score, that same spot for t-score is minus 3.04. So then let's go back here to our p-value. Now they gave us, so now we've got a p-value, we've got a t-score and a p-value. Now let's go back and look at our critical values. So the critical value that we originally were given was 5%. So that will give us a z-score. If we do a normal distribution, mean 0, standard deviation of 1. And we want the probability that x is going to be greater than 5%. That is going to give me a z-score of 1.645. Okay. So now I have my z-scores on my percentages. So now I'm going to do my comparison. So my comparison is the absolute value of my t-score, if that is greater than the absolute value of my z-score, then I'm going to reject the null hypothesis. So let's put that in. If I get the absolute value of my t-score, that's going to be positive 3.04. My z-score was a 1.645. My t-score is greater than my z-score, so that's going to tell me to reject my null hypothesis. Now let's compare my critical level alpha. If that's also greater than my p-value, then that's also going to tell me to reject my null hypothesis. So I was given an alpha of 0.05, and my p-value is 0.0094. So 0.05 is bigger than 0.0094. So that's also going to tell me to reject my null hypothesis. So that tells me that at the 5% level of significance from the sample data, there is sufficient evidence to conclude that the sensory measurements on average are lower after hypnotism, and therefore hypnotism appears to be effective in reducing pain and showing improvement in the patient. Okay, you're going to use the absolute value. So if I have the absolute value, so remember, whenever you take the absolute value, it's going to be positive. Because when I have a left-tailed test, then I'm going to want it to be more extreme. So another way you could do it is, you're going to have your negative, if your negative 3.04 is going to be less than your negative 1.645, then that's also going to tell you to reject. But if you remember, it's the absolute value, then you don't have to worry about your signs. What you're looking for is is the calculated value more extreme than the critical value? And I like to always use the z-scores with the greater sign. Then I just have to remember one formula, and the formula is either true or false. If you start having to remember all of the different variations, then I think it's much easier to get confused. Your alpha is always going to be positive, and your p-values are always going to be positive, so you don't have to worry about that. It's just your z-scores, depending on which side of the graph you are, they might be positive or negative. But if you remember, it's still, you could flip that graph and it's still going to be the same. So like if I have a left-tailed, I want my t-score to be, I want my numbers to be more negative. Okay. Any questions? These are all really good questions. Okay, so that covers everything from Module 10. I know this was kind of a lot, and it was mostly just formulas and examples. So the main thing that you just want to identify is know what the different formulas are, and then identify what type of test that you have, and that's going to help you to know what formulas that you're using. And then on that last one, that pooled proportion, it looks like in your book, based on my notes from when I was taking my notes from your chapter, I'm seeing that I have that formula written 3 different ways. So that's something you want to be really careful about. And then based on how the calculations were done, I believe it should be the sum. You're going to sum your sample successes divided by the sum of the sample size. And I believe I've seen that elsewhere. Like if you watch the Khan Academy, I believe that's shown up there as well.
I hope you have found this helpful. See the links below for additional supports and resources, and be sure to like and subscribe to get the latest videos from Caz Academy. I'll see you at the next video for more statistics and probability.